Imagine you're minding your own business, gazing out into the outer solar system, the quiet suburbs of space, where icy bodies slowly orbit and nothing much happens. Now, suddenly, one of these peaceful wanderers starts throwing cosmic tantrums, not once, not twice, but over and over, like a toddler who just discovered the power of screaming in a supermarket. That's Centaur 29P, an object that astronomers describe, with all their polite scientific vocabulary, as very active, which is just the academic way of saying this comet refuses to chill. 29P is not a neat little rock drifting quietly around the Sunday. No, this thing has been exploding for decades, like the universe's worst surprise party. And here's the kicker. No one really knows why. That's right. With all our telescopes, satellites, and billion-dollar space toys, we're still scratching our heads at a dirty ice ball that acts more dramatic than any reality television star. When 29P goes off, it doesn't just burp politely. No, it glows up to 300 times brighter within hours. It hurls millions of tons of debris into space at speeds faster than sound. Sometimes it erupts 4 times in just 2 days, the astronomical equivalent of chain-smoking fireworks. And there's no obvious trigger. It's not swooping close to the sun like some daredevil comet, nor is it crashing into anything. It just decides to explode, randomly, loudly, spectacularly. So naturally, scientists are both horrified and obsessed, because if the solar system were a classroom, most comets sit in the back, quiet, doodling in their icy notebooks. But 29P? That's the kid flipping desks just to see what happens. And the strangest part? It might be the most active comet in the solar system. Yes, you heard that right. Among billions of space rocks, this one holds the title for sheer cosmic chaos. Only Jupiter's volcanic moon Io beats it, and Io, to be fair, is literally covered in lava-spewing volcanoes. At least Io has an excuse. What's 29P's excuse? Nobody knows. This is the kind of mystery that makes astronomers lose sleep, and maybe you too, if you let me keep whispering about it long enough. Because while most people imagine comets as dusty snowballs quietly orbiting until they fall toward the sun, 29P is busy proving that space is wilder, messier, and far less predictable than we thought. Now, I want you to picture this. 2024 rolls around, and 29P erupts 4 times in 48 hours. From Earth, amateur astronomers watched it flare up like the universe had just lit the biggest cosmic bonfire. The headlines? Comet becomes 300 times brighter overnight, which sounds like something out of bad sci-fi, except it's real. If Earth did that, we'd call it the apocalypse. For 29P, it was just another Tuesday. And here's the part I find hilarious. We've been watching it explode for years, and most of the time it's not NASA, not the European Space Agency, not some billion-dollar telescope that spots it first. Nope. It's usually some retiree in his backyard with a telescope and a lot of patience. Imagine dedicating your career to studying the cosmos, and some guy named Harold with a lawn chair keeps beating you to the punch. Astronomy is humbling like that. But let's step back. What is this unruly thing? Technically, it's called the Centaur. Not the half-horse, half-humankind, though, honestly. That would make more sense than what we've got. Centaurs are weird hybrid objects in space that blur the line between comets and asteroids. They hang out between Jupiter and Neptune in that awkward middle-child region of the solar system. Too icy to be normal rocks, too rocky to be normal comets. Think of them as the teenagers of astronomy, unstable, moody, unpredictable. And none are moodier than 29P. Astronomers first stumbled across it back in 1927, when 2 German skywatchers at Hamburg Observatory noticed something odd while comparing star photographs. At first, it looked like just another comet. But over time, They realized it wasn't following the usual playbook. It wasn't a neat little comet on an elliptical path that occasionally blazed into glory near the Sunday number. 29P was on a nearly perfect circular orbit, just lazily circling the sun like a planet that got demoted before it even had the chance. And yet it explodes, repeatedly, violently, randomly. So here's the puzzle. How do you explain a body that should be calm but isn't? That's where our story begins. With an object that behaves less like a frozen rock and more like a ticking time bomb. And trust me, the deeper we go into this mystery, the stranger it gets. Because Centaur 29P is not just another comet. It's the universe's reminder that sometimes the most boring-looking neighbors hide the most unhinged secrets. The year is 1927. Europe is still trying to shake off the hangover of the First World War. Jazz is making its way across smoky clubs, and in Hamburg, two astronomers are hunched over photographic plates in the observatory. Their names? Arnold Schwassmann and Arno Arthur Wachmann, names that sound like they should belong to rival magicians rather than scientists. They weren't looking for glory. They weren't trying to find a headline-making comet. They were simply comparing a series of glass plates of the night sky, the old-school version of before and after photos when something unusual caught their eye. A faint smudge of light had shifted ever so slightly against the backdrop of stars. That's how Centaur 29P first entered human history. Not with fireworks or trumpets, but as a tiny mark on photographic film. At first, it was filed away as just another comet. Astronomers love comets. They're like celestial visitors, bringing drama and dirty snow to the otherwise quiet suburbs of space. But the more scientists watched 29P, the less it behaved like the usual comet cast. Normally, comets follow long, stretched-out elliptical orbits. They spend most of their time in deep freeze, then swing dramatically near the sun, sprout tails, flare up, and then disappear again for decades, centuries, or sometimes millennia. That's the standard playbook. But 29P didn't read the script. Instead of tracing some eccentric path, it cruised in a nearly perfect circle around the sun, parked out between Jupiter and Saturn, like it was just too stubborn to move along. A comet with a circular orbit? That was weird enough. But then it started to misbehave. It wasn't just its orbit. 29P didn't stay in its lane in other ways either. It was later reclassified as a centaur, a special category of objects that are, quite frankly, the solar system's awkward middle children. They aren't fully comets, but they aren't fully asteroids either. Instead, they sit somewhere in between, embodying the traits of both. Think of centaurs as the mythical mashups of astronomy. The ancient Greeks imagined centaurs as half human, half horse. Astronomers, lacking creativity but armed with precision, borrowed the name for these odd space bodies that seem to live double lives. Like comets, they're icy and sometimes eruptive. Like asteroids, they orbit further out and don't always flaunt dramatic tails. And just like their mythological namesakes, centaurs are unpredictable, dangerous, and a little unhinged. They're cosmically unstable. Most of them won't stay where they are forever. Gravitational nudges from the giant planets eventually push them inward toward the sun, where they either become regular comets, crash into planets, or get slingshotted out of the solar system entirely. In other words, they're passing through. Temporary residents. Tenants on borrowed time. 29P just happened to be one of them. But it had something that set it apart from the crowd. Personality. While most centaurs skulk around quietly, 29P decided to light up the neighborhood, sometimes literally hundreds of times brighter in the span of an afternoon. Now, here's where the story starts to get spicy. The more we studied it, the more it refused to fit into tidy categories. Centaurs are already unstable, But 29P looked like the kind of unstable that requires disclaimers and a safe distance. It wasn't content with simply orbiting. It wanted attention. So picture this. Hamburg Observatory, late 1922. Two astronomers scribbling notes about a faint spot of light they've discovered. Did they have any idea that nearly a century later, their little smudge would be the star of one of the solar system's strangest mysteries? Probably not. To them, it was just one more entry in the cosmic catalogue. To us, it's the beginning of a story about a comet that can't stop exploding. And trust me, this is only the beginning. Because once we trace Centaur 29P back to its true origins, the icy badlands of the Kuiper Belt things get even stranger. To understand Centaur 29P, you have to rewind the cosmic clock. Before it started throwing tantrums between Jupiter and Saturn, it came from a much colder, darker place, the Kuiper Belt. Now, the Kuiper Belt is basically the solar system's attic. It's way out past Neptune, a frozen junkyard filled with icy leftovers from the birth of the planets. Picture all the cosmic debris that didn't quite make it into a planet too small, too irregular, too awkward, just dumped there and forgotten. That's the Kuiper Belt. Pluto lives there. So do thousands of other frozen oddballs. And this is where 29P was born. For millions of years, it stayed in that deep freeze, orbiting the Sun quietly at temperatures close to absolute zero. But the Kuiper Belt isn't a safe forever home. It's more like a waiting room with a trapdoor. Every so often, one of its residents gets nudged by the gravitational bullies of the solar system: Jupiter, Saturn, Uranus, Neptune, and is forced to wander inward. That's how centaurs come to be. They're the in-betweeners. Not fully Kuiper Belt objects anymore, but not yet full-time comets either. They're migrants, drifting inward under the constant influence of gravity's invisible hands. Now, here's the tragic comedy of it all. Centaurs don't last long. In cosmic terms, they're doomed. Their orbits are unstable, destined to change drastically in a few million years at most. A centaur might spiral closer to the Sun and turn into a blazing comet, or crash into a planet. Or, if unlucky, get flung out of the solar system entirely, yeeted into interstellar space like a rejected guest at the galactic party. That's the future 29P faces too. At some point, it will leave its current orbit. In fact, astronomers think it might even get catapulted inward as soon as 2038, thanks to a gravitational shove from Jupiter. Imagine that. In just over a decade, our explosive friend might come even closer to the Sun, setting the stage for even more spectacular fireworks. As if it wasn't dramatic enough already. But even before its next act, 29P stands out from the crowd. Most centaurs skulk around with weird, stretched-out elliptical orbits. Not 29P. Oh no. It struts in an almost perfect circle, like it's trying to pretend it's a planet. And in the universe, being different usually means being unstable. And let's not forget 29P is big. We're talking 60 kilometers wide. To put that in perspective, that's larger than 96% of all known centaurs. If the Kuiper Belt is full of cosmic pebbles, 29P is practically a boulder, and a volatile one at that. So, think about it. An enormous ice ball, kicked out of the Kuiper Belt, wandering in a circular orbit near Jupiter, exploding dozens of times a year for no apparent reason. Sounds like the setup to a bad space thriller, right? But it's real. And it's been happening for almost a century under our watchful eyes. Here's the thing that keeps astronomers awake. Centaurs represent a transitional phase. They're snapshots of what happens to icy bodies as they migrate inward. By studying them, we're not just spying on misbehaving rocks. We're literally watching the solar system's evolution play out in real time. And 29P, with all its chaotic energy, is the loudest, messiest, most fascinating example of this cosmic adolescence. So yes, Centaur 29P came to us from the Kuiper Belt with love. But unlike a love letter, it's less poetry and more chaos. A reminder that space, like life, rarely plays by the rules. And speaking of rules, in the next chapter, you'll see just how doomed centaurs really are. Because if you think 29P is wild now, wait until you hear about what gravity has in store for it. If there's one thing the universe loves, it's reminding us that stability is an illusion, especially when it comes to centaurs. These oddballs, not quite comets, not quite asteroids, live their entire lives on borrowed time. Their orbits aren't the steady, predictable loops of planets. They're fragile, easily nudged, easily disrupted, like a house of cards in a windy room. Centaur 29P is no exception. In fact, its orbit is basically a ticking time bomb. Right now, it cruises along between Jupiter and Saturn on that strangely perfect circle, minding its own explosive business. But here's the kicker: it won't last. Centaurs never do. See, the gas giants, especially Jupiter, are like the cosmic bouncers of the solar system. If you get too close, they'll toss you somewhere else. For centaurs, this usually ends in one of three ways. They get flung inward and become comets, the kind we see with bright tails as they swing past the sunday. They get yeeted outward, banished into interstellar space forever. They collide with a planet or the sun in a final act of fiery drama. Those are the options. None of them involve retirement and peace. And here's where things get even juicier. Astronomers predict that in 2038, Jupiter will likely give 29P a shove that alters its orbit dramatically. That's just around the corner in cosmic time. When that happens, 29P could be pushed into the inner solar system, where the sun's heat will make it even more volatile. Translation: if you think it's explosive now, wait until it gets closer. Now, why does this matter? Because centaurs are basically case studies in instability. By watching them, we get to see in real time how gravitational dynamics sculpt the solar system. Most small icy bodies spend billions of years quietly orbiting in the Kuiper Belt. But once they migrate inward, their lifespans shrink dramatically. Centaurs usually only last a few million years before something drastic happens. They're like cosmic mayflies, flashing briefly before being destroyed or transformed. But 29P is special. It's big, it's active, and it's stuck in that almost circular orbit which makes it feel like a planet wannabe. Yet it's not a planet. It's a 60-kilometer wide drama queen with a self-destructive streak. And because of that, its future is almost guaranteed to be chaotic. Think about it. Sometime soon, possibly in our lifetimes, 29P could become a new comet visible in the night sky, blazing brighter and more unpredictable than anything we've seen before. Or, plot twist, it could get slingshotted out of the solar system entirely, vanishing into interstellar darkness where no telescope will follow. That's the cruel joke of centaurs. They don't get endings. They get fates. And yet, knowing all this, scientists are glued to their telescopes. Because centaurs like 29P aren't just unstable rocks, they're also time machines. Studying them helps us understand the origins of comets, the migration of icy bodies, and even the chaotic dance of the early solar system. In other words, by watching this unstable ice bowl, we're peeking into the past and maybe predicting the future. So yes, Centaur 29P is destined for chaos, but until then, it's our chaos to watch. And the next time it decides to blow its top, somewhere out there, an amateur astronomer with a backyard telescope will probably notice before NASA does. And speaking of things that make 29P different in the next part, we'll zoom in on the two quirks that make this comet stand out from the rest of its Centaur cousins. Spoiler, size really does matter. Every misfit has its quirks. For Centaur 29P, there are two that make astronomers sit up straighter, sip their coffee a little slower, and mutter, well, that's odd. The first quirk, its orbit. Most centaurs trace elongated, lopsided paths around the sun, big stretched ellipses that pull them closer, then fling them far away again. That's what you'd expect of icy bodies that have been kicked out of the Kuiper belt and tossed into unstable territory, but not 29P. Nope. This rebel decided to carve out a nearly perfect circle around the Sunday. It orbits at almost the same distance all year round, about 6 times farther from the Sun than Earth. Now you might think, circular orbit, that sounds boring. But here's the twist. Boring should mean predictable. If it's always the same distance from the Sun, it should absorb the same amount of solar radiation all the time. That means no dramatic temperature swings, no sudden flare-ups, just a quiet, icy existence, like a thermostat stuck on low. And yet it explodes. Repeatedly, violently, randomly. It's like owning a refrigerator that catches fire once a week. You'd expect peace. You get chaos. The second quirk? Its size. 29P isn't just another pebble drifting in the cosmic dock. It's a giant, at least by Centaur standards. Measuring about 60 kilometers across, it's larger than 96% of all known centaurs. To put that into human terms, if most centaurs are like compact cars, 29P is a lumbering 18-wheeler barreling down the space highway, and an unstable one at that. This size matters. Big bodies retain heat differently. They hold onto volatile materials longer. They can trap gases deep inside for millions of years, letting pressure build until BAM outbursts happen. So the very thing that makes 29P so imposing may also be the thing that keeps it so unpredictable. And then there's the most obvious quirk of all. It's an exploder. While most centaurs play it cool, 29P is the cosmic drama queen, averaging around 30 eruptions a year. That's 2 or 3 explosions every month, on average. Imagine having a neighbor who throws fireworks shows without warning, charming at first, exhausting after a while. 40% of these eruptions don't follow any schedule at all. They just happen sudden, bright, and wild. Within 2 or 3 hours, the comet can surge to peak brightness, shining hundreds of times brighter than usual. Then, just as suddenly, it fades back into icy obscurity, leaving astronomers both thrilled and exasperated. And sometimes, the explosions come in rapid-fire bursts. In 2024, for instance, 29P erupted 4 times in just 48 hours, briefly becoming 300 times brighter than normal. That's not a comet behaving badly. That's a comet behaving like it's auditioning for a role in a Michael Bay film. So here's the summary. Perfectly circular orbit. Enormous size. Explosions, like clockwork, except when they're not. In short, 29P is the centaur that refuses to follow the rules. It's like the cosmic equivalent of someone who shows up to every wedding in a clown suit, unforgettable, confusing, and impossible to ignore. And yet, as strange as all that sounds, the story only gets stranger. Because once you start counting these explosions and looking at the patterns, you realize this isn't random chaos. This is chaos with flair. And sometimes chaos with headlines. Which brings us neatly to the next chapter. The sheer statistics of 29P's outbursts, and how one comet manages to outdo even the most volcanic worlds in our solar system. Alright, let's talk numbers. Because when it comes to Centaur 29P, the statistics aren't just impressive, they're absurd. If most comets occasionally flare up like a cheap lighter, 29P is the industrial fireworks factory that keeps blowing its roof off. On average, it erupts around 30 times a year. That's not a typo. 30. That's nearly once every 12 days. Astronomers joke that it's the only comet where, if you miss an outburst, don't worry, just wait a week. But it's not just the frequency that's staggering. It's the violence. Take the 2024 event. In the span of just 48 hours, 29P erupted 4 separate times. Each explosion made it shine hundreds of times brighter than normal. For a brief window, it looked less like a humble comet and more like a distant supernova cosplaying as a disco ball. 2 years earlier, it launched more than 1 million tons of debris into space. 1 million tons, and not lazily drifting. Either this material was hurled out faster than the speed of sound. That's like uncorking the most pressurized champagne bottle in the solar system and watching it spray icy foam across millions of kilometers. And the best part? That single outburst triggered 2 more smaller ones, 5 and 7 days later. Apparently, when 29P explodes, it likes to do encores. And it gets wilder. In September 2021, the comet underwent the largest eruption in 40 years. It didn't just flare up once. It blew its top 5 times in a row. Imagine a volcano erupting multiple times in 1 week. Except instead of molten lava, it's spewing icy gas and frozen dust across deep space. That's 29P for you. Relentless, unpredictable, and just a bit showy. Here's the kicker though. Despite how spectacular these events are, professional astronomers aren't always the first to spot them. Nope. Most of the time, it's amateurs who catch the action. Some hobbyist in Spain, or a retiree in Arizona, peering through a modest telescope, will notice 29P glowing brighter and post about it online before the big observatories even know what happened. Think about that for a second. We've got billion-dollar space telescopes orbiting Earth, and yet a guy in his backyard with a cup of coffee might be the first to raise his hand and say, excuse me, I think that comet just exploded again. It's humbling and hilarious. So, let's recap the scorecard. Roughly 30 eruptions a year, up to 300 times brighter in hours, over 1 million tons of debris in a single outburst, record-setting mega eruption in 2021 with 5 blasts in a row, and most of the discoveries made by amateur astronomers. At this point, Centaur 29P isn't just a comet, it's practically a performance artist, a chaotic, icy diva that refuses to be ignored. But here's the problem. While the explosions are spectacular, they don't follow any obvious pattern. There's no neat schedule, no obvious connection to its orbit, no warning signs you can rely on. For decades, astronomers have tried to predict when the next eruption will happen, and, mostly, they've failed. It's like trying to predict when a cat will knock something off the table. You know it will happen, you just don't know when. And yet, this unpredictability is exactly what makes 29P so fascinating. Because if we can figure out what triggers these outbursts, we might unlock a deeper understanding of how icy bodies behave in the outer solar system. And, as you'll see in the next chapter, sometimes the best discoveries don't come from billion-dollar instruments at all, but from hobbyists with backyard telescopes who just really love watching the sky. Here's one of my favorite ironies in all of astronomy. The universe doesn't always reveal its secrets to the billion-dollar telescopes. Sometimes, it whispers first to the guy in the backyard with a folding chair, a thermos of coffee, and a telescope bought second-hand off eBay. Centaur 29P is living proof of that. Despite being one of the most dramatic objects in the solar system, many of its most spectacular outbursts weren't first spotted by Hubble or Keck or any of the shiny professional observatories. Nope, they were caught by amateur astronomers. Take September 2021, for example. That was when 29P decided to put on its biggest show in 40 years. It erupted 5 times in a row, practically yelling into the void, "Look at me!" But who noticed first? Not NASA, not the European Space Agency. It was hobbyist skywatchers. Ordinary people with ordinary telescopes, scanning the skies because, well, they just loved it. When the news trickled up to the professional community, scientists scrambled to secure precious telescope time for a closer look. That's not as easy as it sounds. You can't just point Hubble or another major instrument at your favorite exploding ice ball on a whim. Time on those machines is as competitive as trying to book a last-minute table at a Michelin star restaurant. And just as expensive. Yet here's the beautiful part. In astronomy, amateurs and professionals actually rely on each other. Professionals have the big tools, but amateurs have flexibility. They're free to scan the skies night after night. No committees, no grant proposals, no paperwork, just passion. And sometimes passion gets there first. 29P, in particular, has built itself a reputation as the amateur's comet. Its eruptions are sudden and dramatic, which makes them ideal for backyard astronomers. The moment it brightens, a message goes up on astronomy forums. 29P just popped again. And within hours, observatories around the world are pivoting to catch the fading afterglow. It's almost funny, if you think about it. We spend billions building the James Webb Space Telescope to catch the faintest whispers of ancient galaxies, and meanwhile, a retired dentist in Arizona can wake up the entire astronomy community with a casual email. By the way, that weird centaur exploded again. And this isn't new. For decades, amateur astronomers have been the first to catch 29P's fireworks. Professionals, of course, step in to analyze the details, the gas composition, the outflow speed, the brightness curve. But the alerts? Those often come from people who just happen to be watching. It makes 29P feel like a communal project, a reminder that science isn't always about who has the fanciest equipment, but who pays attention. And in a way that fits the comet's personality. 29P doesn't play by the rules. So of course, it wouldn't reveal its secrets to bureaucratically scheduled telescopes. Instead, it winks at the amateurs. The ones stubborn enough to sit outside at 3 a.m. with a telescope pointed at the cold edge of the solar system. And that's part of why 29P is so beloved in the community. It's messy, unpredictable, wild, and it keeps giving both amateurs and professionals reasons to collaborate. Some comets flare once a century. 29P flares all the time. It's like the universe designed it as a gift for the people who never stopped looking up. But of course, even when the pros do get their shot, things don't always go to plan. In fact, once upon a time, scientists thought they finally had their big chance with Hubble. And then the universe pulled one of its favorite tricks, trolling us. So, picture this. Centaur 29P has just gone through one of its dramatic meltdowns, blasting tons of gas and dust into the void, like it was auditioning for the role of best fireworks finale in the cosmos. The astronomy community? Buzzing. Finally, here was the chance to study one of these eruptions in detail with the most powerful eye in orbit. The Hubble Space Telescope. Getting Hubble time is no small feat. You don't just send an email saying, "Hey, could you point that billion-dollar telescope at my favorite exploding snowball?" No, it's months of proposals, committees, justifications, and competition against every other astronomer on Earth, who also wants a piece of that telescope pie. But when 29P flared in 2021, the stars seemed to align. Approval was given. Observers held their breath. Finally, we'd catch this icy diva mid-outburst. Except, the universe had other plans. The day before Hubble was scheduled to focus on Centaur 29P, the telescope suffered a technical glitch. It went into protective safe mode, shutting down science operations. Translation: The cosmic show went on, but Hubble was too busy sulking to watch it. If you've ever booked tickets to see your favorite band, only for the lead singer to lose their voice the night before, you know the pain. Astronomers waited years for this chance, and the universe ever the trickster pulled the rug out at the last second. And here's the part that really stings. Eruptions like that don't wait around. 29P doesn't care about your billion-dollar telescope schedules. It doesn't care about your carefully written grant proposals. When it blows, it blows. And if you miss it, tough luck. You'll just have to wait for the next unpredictable outburst. It was a cosmic prank, honestly. The comet flared. The amateurs saw it. The pros got their paperwork. The most expensive telescope in orbit blinked. Moments like this remind us that astronomy is not just about data. It's about patience, humility, and sometimes frustration. We can map galaxies billions of light years away, but one icy troublemaker between Jupiter and Saturn still manages to troll us like a cosmic comedian. But setbacks didn't stop the pursuit. Scientists knew that if they couldn't get Hubble in on the action, maybe other instruments or other methods could help piece together the mystery. Because the question still loomed: what exactly causes these violent eruptions? And that's where things start to get even stranger. Because the answer, it turns out, isn't fiery volcanoes or cosmic collisions. It's something even more bizarre. Volcanoes made of ice. All right, here's where the story takes a turn from cosmic fireworks to what in the frozen underworld is that? Because if you thought Centaur 29P was powered by normal volcanoes, hot magma, molten rock, rivers of fire, think again. Out there in the frigid outer solar system, fire isn't the star of the show. Ice is. Scientists eventually realized that 29P behaves like a cryovolcanic comet. That's a fancy way of saying it has ice volcanoes. Yes, volcanoes that erupt not with lava, but with a strange, slushy cocktail of frozen gases, dust, and ammonia. Imagine a Slurpee machine from hell, one that explodes without warning, and you're getting close. Here's how it works. Deep inside 29P, you've got a mixture of volatile materials: carbon monoxide, carbon dioxide, nitrogen, all locked up in ice. The comet's outer crust is a fragile, brittle shell. Over time, the sun's faint radiation seeps in. Not much, remember. This thing is 6 times farther out than Earth, but enough to start sublimating those ices inside, turning them straight from solid to gas. As the gas builds, pressure starts to rise beneath the surface. Think of shaking a soda bottle and leaving it capped. At some point, the pressure becomes too much for the thin crust to handle. Crack. The shell gives way, and all that trapped gas and ice come blasting out in a spectacular eruption. That's what we see from Earth: sudden outbursts of brightness as material jets into space, forming a temporary atmosphere, a coma, around the comet. And when astronomers first pieced this together, it felt like a revelation. Oh, so these aren't random explosions. They're ice volcanoes. Now, don't let the word ice fool you into thinking this is gentle. Cryovolcanic eruptions are violent. When 29P goes off, it can eject material at speeds faster than the speed of sound. A mix of frozen water, carbon dioxide, salts, ammonia, all hurled out in plumes that would dwarf Mount Vesuvius. For a brief moment, this icy rock out in the dark becomes one of the most active worlds in the solar system. And it doesn't end there. The material doesn't all escape into space. Because 29P is big, much bigger than most comets, its gravity pulls a lot of that debris back down. It falls onto the surface, settles, and forms a new crust. Sounds peaceful, right? Wrong. That new layer can seal off other pockets of gas beneath it. Days later, when the pressure builds again, bam! Another eruption. This is why 29P often erupts in sequences. One big outburst sets off aftershocks like lighting the fuse on a chain of fireworks. We saw this in 2021, when a giant eruption was followed days later by smaller ones. It's not a coincidence. It's a cycle of crust breaking, resealing, and rebreaking. So yes, Centaur 29P is a cryovolcanic world, an ice volcano machine. But even with this theory, things don't quite add up. Because if it's just solar heating causing sublimation, and a thin crust cracking now and then, we should see fairly regular eruptions. Predictable ones. And we don't. Instead, we get chaos, unscheduled blasts, wild differences in intensity, sometimes nothing for weeks, other times 4 in 2 days. Like a soda bottle that sometimes hisses gently and other times explodes in your face. So even though the ice volcano model explains a lot, it still leaves us with a mystery. Why does 29P erupt so erratically? What's fueling the madness when, by all logic, it should be more well-behaved? That's the puzzle scientists kept chewing on. Because in theory, 29P should be boring. In practice, it's one of the wildest shows in the solar system. And in the next part, we'll look closer at those chain reactions, the aftershocks, the echoes of eruptions that make 29P seem less like a rock and more like a cosmic firecracker that refuses to stop. So we've got our icy soda bottle, shaking away in the cold darkness of space, popping its lid whenever the pressure inside gets unbearable. But here's the thing. Centaur 29P doesn't just erupt once and then call it a night. No. Like a diva who refuses to leave the stage, it often gives us encores. Astronomers noticed that after a major eruption, 29P has this habit of setting off smaller, secondary explosions days later. Think of it like cosmic aftershocks. One big blast is followed by little bursts, echoes of the original event. The comet just can't help itself. Once it starts, it keeps going. Why? Well, remember how I said not all of the debris escapes? Because 29P is a heavyweight 60 kilometers wide, a lot of that icy shrapnel falls right back down onto the surface. It doesn't just sit there innocently. When it lands, it creates a new crust, sealing off still bubbling pockets of gas below. It's like slamming the lid back on a pot that's still boiling. So, the pressure builds again, and a few days later, crack! Another eruption. Not as big as the first one, but enough to remind us that 29P isn't done performing. This cycle can repeat one big outburst, followed by 2 or 3 smaller ones in quick succession. A cosmic encore, whether we asked for it or not. Take the 2021 mega eruption, 5 outbursts in a row. Astronomers watched in awe, and probably with a bit of exhaustion. The comet brightened dramatically, dimmed, brightened again, and so on like a flickering lantern in the dark. Each time, gas and dust spewed out, forming a hazy cloud around the nucleus. For days, 29P looked less like a comet and more like a smoldering campfire that refuses to go out. And that's part of what makes it so fascinating. Most comets are content with one dramatic flare-up when they swing by the Sunday 29P. It likes to milk the moment. A single eruption becomes a series, like a Netflix show that just got renewed for multiple seasons. Now, imagine being an amateur astronomer tracking this thing. You log one eruption, feel proud of yourself. Then a few days later, it's gone off again. Back to the telescope, back to the notes, back to the astronomy forum where hobbyists post. She's at it again. And this pattern tells us something important. It shows that 29P's crust isn't just cracking randomly. There's a whole dynamic process happening under the surface. Pockets of gas get trapped, layers form and reform. One eruption sets the stage for another. The comet isn't chaotic just for fun, it's chaotic because its internal structure keeps recycling stress. But even with this understanding, there's a nagging question. If 29P is on a nearly perfect circular orbit, always the same distance from the Sun, why do these eruptions happen at such irregular times? Shouldn't the heating, the gas release, the pressure, shouldn't it all be consistent? And that, my friend, is where the story takes yet another twist. Because the circular orbit that should make 29P boring is actually the very thing that makes its behavior so baffling. Here's the paradox that keeps astronomers awake at night. Centaur 29P orbits the Sun in an almost perfect circle. And that's weird, because in theory, a circular orbit should make life boring. It means 29P is always about the same distance from the Sun, roughly 6 times farther than Earth. No dramatic swings in heat, no fiery close approaches, no freezing retreats into deep space, just steady, predictable sunlight, the celestial equivalent of living in a climate-controlled room. So if the heating is consistent, the eruptions should be consistent too, right? Smooth, regular bursts of gas and dust. A cosmic metronome. Tick-tock bang, tick-tock bang. Easy. Except 29P doesn't do that. Instead, it behaves like a roommate who swears they'll keep quiet, but then decides to start vacuuming at 3 a.m. Outbursts come at random. Some are small, some are massive, some come in clusters, and others leave long gaps of silence. It's as if the comet has moods. This is where the frustration lies. With comets on elliptical orbits, the logic is clear. They flare up when they swing near the Sun, when the heat ramps up, when ice turns to gas more violently. Predictable. But 29P? It's basically getting the same amount of sunlight all year round. So why the tantrums? One idea is that the culprit isn't just the Sun's heating, but 29P's own internal structure. Remember that thick crust that cracks open with every eruption? It's uneven, fragile, and constantly reforming. Beneath it, different pockets of volatile ice may be closer to the surface in some regions than others. That means local conditions, not orbital ones, might control when and where eruptions happen. Another idea focuses on rotation. 29P takes a leisurely 57 days to spin once on its axis. That's incredibly slow compared to most comets. Some scientists think this sluggish rotation could be key, as different regions face the Sun over those long days. Subtle heating differences might trigger eruptions. It's less about the orbit, more about where the sunlight falls and how the crust handles it. Still, none of these theories fully explain the randomness, and the unpredictability is maddening. Because while astronomers can chart the orbit of a comet to the second, they can't say when 29P will blow again. It's like knowing exactly where your toaster is in the kitchen, but never knowing when it'll decide to launch bread across the room. This mismatch between the boring orbit and the chaotic activity is what makes 29P such a scientific treasure. It forces us to admit that the solar system isn't always neat, logical, or predictable. Sometimes, even when all the conditions seem stable, the result is pure mayhem. And yet, amid the randomness, a few patterns have started to emerge, little hints that maybe 29P isn't as unpredictable as we thought. Maybe, just maybe, there's a rhythm to the madness. Here's the thing about chaos. Humans can't stop trying to find patterns in it. We stare at clouds and see castles, look at stars and draw constellations, and when faced with Centaur 29P, astronomers inevitably asked, is there some kind of rhythm hiding in all this madness? Turns out, maybe. For decades, researchers logged every eruption they could catch. At first glance, it looked random, like popcorn kernels bursting unpredictably in a pan. But when they dug deeper, something curious appeared. A faint beat, almost like a drum buried under static. The key might lie in 29P's rotation period. Unlike Earth, which spins once every 24 hours, or Jupiter, which whips around in just 10 hours, 29P is slow, painfully slow. It takes about 57 days to spin once. Imagine a world where one day lasts nearly 2 months. That sluggish rotation means some regions of its surface spend weeks basking in sunlight, while others endure weeks of darkness. Astronomers notice that big eruptions seem more likely to happen every 52 to 60 days, suspiciously close to that rotation cycle. Maybe when a weak spot rotated back into sunlight, it got just warm enough to crack, releasing the gas trapped beneath. But it wasn't just that. Smaller outbursts showed up too at intervals of roughly 30 days and 90 days. It was almost like 29P had multiple cycles playing at once, like overlapping rhythms in a jazz piece. Not perfectly regular, but repeating just enough to make scientists wonder, is this comet not random at all, but seasonal? Think about that. Seasons on Earth are caused by our tilt and orbit around the Sunday. But 29P's seasons wouldn't be about orbit. Remember, its orbit is circular. Instead, they might be caused by how slowly it rotates and how its crust reshapes after every eruption. In other words, the comet might have its own bizarre internal calendar. Of course, the problem is that, while the timing hints at patterns, the intensity doesn't. One eruption might be a tiny puff, the next, a city-leveling blast, if it were anywhere near us, that is. It's like living with a roommate who sometimes whispers and sometimes sets off fireworks in the living room. Same timing, wildly different results. Still, these cycles gave astronomers hope. If you can spot even a vague rhythm, maybe you can predict the next big event. And for scientists, prediction is everything. Without it, you're just waiting helplessly for the universe to throw surprises at you. With it, you get to say, "Aha, called it." And that feels a lot better. For years, the search continued. Could we finally pin down 29P's rhythm? Could we predict its next tantrum before it happened? And then, in 2023, for the very first time, the prediction came true. For decades, Centaur 29P had been trolling astronomers. They'd point their telescopes, watch it for hours, and then the moment they looked away, boom. Another eruption, gone before they could capture the juicy details. Predicting 29P's tantrums felt about as realistic as predicting when your cat will knock something off the counter. You know it's coming, you just don't know when. But in April 2023, something extraordinary happened. For the first time, astronomers called it in advance. Here's how it went down. Scientists had been monitoring the faint glow of gas around 29P's nucleus, its so-called coma. Over weeks, they noticed the light was fading, dimmer than they'd ever seen before. That suggested one thing. The comet wasn't releasing much gas, which meant pressure was building inside like a soda can left in the sundae. So they made a bold prediction. 29P was about to blow. And sure enough, that very same day, the comet erupted. Not a giant, world-shaking blast, but a definite, measurable outburst, enough to prove they'd finally cracked part of the code. For the scientific community, this was a milestone. After nearly a century of randomness, 29P had finally been caught red-handed before the explosion. Imagine the relief. It was like finally guessing the punchline of a joke that's been tormenting you for years. Of course, this didn't mean the mystery was solved. Far from it. One successful prediction doesn't unravel decades of chaos, but it was proof that 29P's behavior wasn't entirely unknowable. That maybe, hidden beneath the noise, there were real physical processes we could anticipate. And for scientists, that's gold. Prediction is the difference between superstition and understanding. It turns "weird comet does random stuff" into "here's a model that explains why it happens." It's the first step toward pulling the curtain back on 29P's strange inner life. Better yet, this breakthrough came at a time when humanity had a new ace up its sleeve: the James Webb Space Telescope. With Webb's incredible instruments, astronomers were about to look closer at 29P than ever before, and what they found would shake up our assumptions all over again. If astronomy were a movie, the James Webb Space Telescope would be the big-budget sequel everyone had been waiting for. Bigger mirrors, sharper vision, infrared superpowers — it's the upgrade astronomers had dreamed about for decades. And when Webb finally launched, one of the first cosmic divas to step into its spotlight was, of course, our unpredictable troublemaker, Centaur 29P. Up until this point, scientists had been arguing about what exactly powered 29P's endless tantrums. Carbon monoxide, CO, had long been the prime suspect. Every time astronomers pointed radio telescopes at the comet, they picked up signs of CO gas streaming away, like exhaust fumes from a leaky engine. The theory went, CO was the main fuel for the explosions. Case closed. Except Webb, with its cutting-edge instruments, decided to complicate the story. Using its near-infrared spectrograph, Webb zeroed in on 29P's outbursts. And what did it find? Not one, but two jets of carbon monoxide, shooting out in different directions, one toward Earth and one toward the north. Okay, fair enough. CO was still in the game. But then came the real twist. Webb also detected carbon dioxide, CO2, for the very first time on 29P. Not just a little, enough to prove that CO wasn't acting alone. In fact, Webb revealed two jets of carbon dioxide, blasting out from the north and south. Suddenly, the picture shifted. Instead of one neat explanation, CO drives the eruptions, we had a messy duet of gases, each erupting from different regions. And that led to an even stranger idea. If 29P is spewing out multiple jets of different compositions, maybe it isn't a single uniform object at all. Maybe, just maybe, it's actually a clump of smaller objects stuck together, each with its own stash of frozen gases, venting in its own way. In other words, 29P might be a Frankenstein comet. For astronomers, this was both thrilling and maddening. On one hand, hooray, new data. On the other, the mystery had only deepened. Instead of narrowing the cause of the eruptions, Webb had added more suspects to the lineup. Still, this was a breakthrough moment. For the first time, we had hard proof that carbon dioxide was playing a role. The comet wasn't just a one-trick pony. It was a full orchestra of volatile gases, and the performance was far less predictable than anyone thought. But then another problem reared its head. CO and CO2 are both extremely volatile. If they were hanging out near the comet's surface, they should have evaporated ages ago. So how exactly were they still hanging around, fueling eruptions in 2024? To answer that, scientists turned to one of the weirdest substances in the solar system: amorphous ice. Here's the head-scratcher. Carbon monoxide shouldn't still be there. CO is one of the most volatile ices in the cosmos. It evaporates at temperatures as low as 25 Kelvin. To put that in perspective, that's just 25 degrees above absolute zero. If CO were sitting anywhere near the surface of Centaur 29P, it would have escaped millions of years ago, long before humans invented telescopes to gawk at it. And yet, every time 29P erupts, we detect fresh CO pouring out. So where's it hiding? The obvious answer is deeper underground, buried, trapped, preserved somehow beneath layers of crust. But that just raises another question. What's keeping it locked in for so long? That's where the concept of amorphous ice comes in. And trust me, this stuff is weird. Most of the ice we know here on Earth is crystalline. Snowflakes, glaciers, ice cubes, they all have neatly arranged molecules packed into structured lattices. Amorphous ice, on the other hand, is the cosmic oddball. Its molecules are jumbled, unstructured, messy. Think of it like the difference between a neat stack of bricks and a pile of Lego spilled on the floor. Why does this matter? Because amorphous ice can trap gases inside its structure. Carbon monoxide, carbon dioxide, nitrogen, all of them can be locked away in the gaps between those disordered water molecules, preserved like ancient insects caught in amber. Here's the catch. Amorphous ice isn't stable forever. Once it warms above 77 Kelvin, it starts transforming into crystalline ice. And when that happens, the trapped gases are released in sudden, powerful bursts. Sound familiar? Yep. That's exactly the kind of behavior we see from 29P. The idea is that deep inside the comet, patches of amorphous ice are slowly converting into crystalline ice as the comet's interior warms. Each conversion acts like popping bubble wrap on a cosmic scale, releasing pockets of gas that shoot toward the surface, crack the crust, and explode into space. This would explain why 29P still has fresh CO, despite being closer to the Sun than its birthplace in the Kuiper Belt. Back when it was way out there, temperatures were frigid enough, around 30–40 Kelvin, for amorphous ice to form and trap gases. As it drifted inward over the last 10 million years, it warmed to about 115 Kelvin, hot enough for crystallization to begin. But here's the kicker. Because 29P is so huge, that process is still ongoing. Smaller centaurs, just a few kilometers across, would have finished crystallizing ages ago, releasing all their gases in one dramatic phase. They're predictable, boring, all tapped out. But a 60-kilometer monster like 29P? It's still halfway through its transformation, meaning huge reservoirs of CO are still locked inside, waiting to blow. This theory doesn't just explain the presence of CO. It explains the erratic nature of the eruptions. Different regions of the comet's core are crystallizing at different rates. Some are quiet, others are primed to explode. It's like having a building wired with fireworks, but only certain rooms go off at a time. So carbon monoxide isn't just a fuel, it's a clue, a sign that 29P is in the middle of a slow-motion transformation, a cosmic puberty that's been dragging on for tens of millions of years. And like any teenager, it's messy, unpredictable, and prone to outbursts. But if amorphous ice is really driving the show, that raises an even bigger question. Just how long will this explosive phase last? Let's slow down for a second and appreciate just how bizarre amorphous ice really is. Because if you're imagining the stuff in your freezer at home, neat, solid cubes clinking in a glass, forget it. That's crystalline ice, orderly and elegant. Every water molecule stacked like bricks in a wall. Amorphous ice? That's chaos frozen solid. It's water molecules all jumbled together. No symmetry, no structure, no neat patterns. More like a cosmic sponge, riddled with gaps where gases like carbon monoxide and carbon dioxide can hide out for millions of years. And here's the kicker. Under the right conditions, amorphous ice isn't just unusual, it's unstable. The moment temperatures creep above 77 Kelvin, still ridiculously cold by Earth standards, but warmer than deep Kuiper Belt conditions, it starts converting into crystalline ice. And when it does, all those gases trapped inside get kicked out in a rush. Picture popping bubble wrap. Except each bubble is made of frozen carbon monoxide, and when it bursts, it releases enough pressure to crack open kilometers of crust. That's what astronomers think is happening inside Centaur 29P. Back when 29P lived in the Kuiper Belt, it was safe. Temperatures there hover between 30 and 40 Kelvin, so everything stayed amorphous. The gases remained comfortably trapped. No drama. But when gravitational nudges shoved it inward, closer to the sun, the heat crept up. Slowly, steadily, patches of amorphous ice began crystallizing, releasing gas in bursts. That's the hidden engine driving its fireworks show. And here's where the size factor comes in. Smaller centaurs 1 to 6 kilometers across crystallize completely within just a few million years. They're like small ice cubes that melt quickly on a warm day. By the time they reach 29P's current orbit, they're basically all crystalline, boring, and predictable. No more surprises. But 29P? It's a 60-kilometer giant. A glacier compared to the ice cubes. At its size, full crystallization takes far longer, between 60 and 100 million years. Which means right now, 29P is only about halfway through the process. Scientists estimate maybe 50–65% of its amorphous ice has crystallized. The rest? Still sitting there, locked and loaded, waiting for the right moment to let go. This is huge, because it means 29P is literally in the middle of a cosmic transformation. It's not done being weird. It's not done exploding. It has tens of millions of years of chaos left in the tank. And the implications go even deeper. As the conversion from amorphous to crystalline continues, the comet's interior actually shrinks in volume. The denser crystalline ice takes up less space than the fluffy, porous, amorphous ice. That creates stress inside the nucleus. Imagine a giant sponge collapsing in on itself. Cracks form, caverns open, sinkholes collapse. Each structural failure could trigger yet another eruption. So now we have not one, but two engines for chaos. The chemical release of trapped gases as amorphous ice crystallizes. The physical collapse of the comet's interior as it reshapes itself. No wonder it behaves like the drunk uncle of the solar system. It's literally falling apart on the inside while venting pressurized gases on the outside. Which leaves us with a haunting thought. If 29P is still halfway amorphous, how many more surprises are buried within it? And could the very process of turning crystalline be the reason behind its most violent outbursts? That's the riddle scientists are still chewing on. And the next part of our journey dives right into that question. What happens when the comet's very structure starts betraying itself? Let's rewind the tape on Centaur 29P's life story. Long before it became the drama queen of the solar system, it was just another frozen body sitting quietly in the Kuiper Belt, that vast ring of icy debris beyond Neptune, the leftovers of planet building. Temperatures out there hover around 30–40 Kelvin. That's 233 degrees Celsius. At that level of cold, nothing stirs. No sublimation, no eruptions, no chaos, just silence and ice. In those conditions, water freezes not as the neat crystalline ice we know, but as amorphous ice, the messy kind that acts like a sponge for gases. Carbon monoxide, carbon dioxide, nitrogen all trapped inside. Billions of years went by, and 29P stayed in deep freeze, perfectly preserved. But the Kuiper Belt is not a forever home. Gravity, especially the heavy hand of Jupiter and Saturn, likes to reshuffle orbits. At some point in the last 10 million years, 29P got nudged inward. Slowly, it drifted away from the Kuiper Belt's freezer and into warmer territory. Not tropical warm, let's not exaggerate, but warmer compared to what it was used to. By the time it settled into its current orbit, about 6 times farther from the Sun than Earth, the average temperature had climbed to around 115 Kelvin, 158 degrees Celsius. Now, to us, that's unimaginably cold. But to 29P, it was like being shoved into an oven. That's warm enough to start turning amorphous ice into crystalline ice. And with that change came gas release, pressure buildup, and eventually the eruptions we see today. Here's the fun part. This transformation doesn't happen all at once. Think of it like baking a frozen lasagna. The outer layers heat up and start bubbling long before the inside thaws. Same with 29P. The crust and shallow layers feel the sun's touch first, crystallizing and releasing gases. Deeper inside, though, the ice is still amorphous, still holding its volatile secrets. So eruptions don't come from one neat layer, they come from pockets at different depths, all converting at their own pace. And that's why 29P is so chaotic. One region of its core might be quiet, another boiling with trapped gas, another collapsing under its own weight. From Earth, what we see is a comet that looks unpredictable. From 29P's perspective, it's just the messy reality of being caught mid-transformation. Scientists ran the numbers to estimate just how long this metamorphosis takes. For small centaurs, 1 to 6 kilometers wide, the process wraps up quickly, anywhere from 100,000 years to a few million years. By the time they reach 29P's orbit, they're stable, predictable, and boring. But 29P is a behemoth. At 60 kilometers wide, it takes exponentially longer to crystallize fully, anywhere from 60 to 100 million years, which means what we're witnessing right now is just the halfway point. Roughly half its ice is still amorphous, still primed to release gas in sudden, violent bursts. So what does that mean for us? It means 29P isn't an exception. It's a glimpse into a process we rarely get to observe. It's a natural laboratory, showing us what happens when the frozen relics of the solar system start waking up. And unlike most centaurs, which go quietly, 29P is big enough to stretch this drama out for tens of millions of years, lucky for astronomers, unlucky for anyone who craves predictability. In short, 29P was born in a freezer, dragged into an oven, and now spends its days cracking, venting, and collapsing under the strain of its own transformation. And the more it changes inside, the stranger the surface becomes. Sinkholes, landslides, fractures, all of which feed right back into its cycle of explosions. Which brings us to the next act of this icy tragedy. What happens when the very bones of the comet start betraying it? If there's one thing the universe loves to remind us, it's that size really does matter. And when it comes to Centaur 29P, its sheer bulk is the key to why it hasn't burned out yet, why it keeps exploding like a cosmic firecracker while its smaller cousins have already fizzled. Let's put this into perspective. Most centaurs we've studied are small, just a few kilometers across. Cute little ice marbles, tossed inward from the Kuiper belt. They don't hold on to their secrets for long. Once they start warming up, the amorphous ice inside them crystallizes completely in a blink of cosmic time, maybe a few 100,000 years, a couple million at most. By the time they're in 29P's neighborhood, they're basically spent. All their gases vented, all their drama over. Predictable, tame, forgettable. Now compare that with 29P, a hulking 60-kilometer wide giant. Suddenly everything changes. At this scale, the process of crystallization doesn't wrap up quickly. It drags on for tens of millions of years. Estimates suggest that while small centaurs complete the transformation in 0.1 to 6 million years, 29P needs somewhere between 60 and 100 million years. That's the difference between lighting a match and watching a log smolder for hours. And the kicker, it's not finished yet. Right now, scientists think only about 50–65% of 29P's amorphous ice has crystallized. That means a huge fraction of its interior is still locked up, holding volatile gases like CO and CO2 in reserve. So every eruption we see is basically a teaser. The real drama? It's still unfolding. This is why 29P is such an outlier. Most centaurs don't last this long in such an active state. But because of its size, 29P has stretched its adolescence into a multi-million-year fireworks display. It's the teenager of the solar system that never grows up, constantly slamming doors and blasting music, while its siblings have long since settled down. And size doesn't just affect the timing. It also changes the physics of each eruption. With a larger mass, 29P has stronger gravity compared to other comets. That means a lot of the material it blasts out doesn't actually escape. Instead, it rains back down, coating the surface, sealing off vents, forming new crusts. Those crusts trap gases again, which sets the stage for another explosion days or weeks later. It's a self-recycling system of chaos, made possible by sheer scale. So yes, size matters. Without its bulk, 29P would have crystallized long ago and joined the ranks of boring centaurs. Instead, it's still halfway through its transformation, still rattling astronomers with unpredictable eruptions, still rewriting what we think we know about icy bodies. And the bigger it is, the messier the consequences. Because when a giant like this starts reshaping itself, the stress inside builds up in ways that small bodies never experience. Cracks form, caverns collapse, sinkholes swallow surface layers whole. Every structural failure is a potential trigger for yet another eruption. Which brings us neatly to the next act in this slow-motion disaster. The comet's own interior starting to betray it, cracking and collapsing as it tries and fails to stabilize. Here's where the story of 29P turns from wild fireworks to something darker, because what's happening inside this comet isn't just about ice turning to gas. It's about the very bones of the comet giving way under the strain of transformation. Remember how we talked about amorphous ice converting into crystalline ice? That shift isn't just about releasing trapped gases. It also changes the volume of the ice. Crystalline ice is denser, more compact, which means that as big chunks of 29P's interior crystallize, the comet literally shrinks in places. Not by much, but enough to cause stress. Cracks form, caverns buckle. Think of a sponge collapsing after being squeezed dry. For a comet 60 kilometers wide, that's not just a little tremor. That's landslides, cave-ins, sinkholes opening up. Whole sections of the crust could collapse without warning. And each collapse isn't quiet. It exposes fresh layers of volatile material to sunlight, ignites new outbursts, and starts the cycle all over again. So now, scientists think some of 29P's most violent eruptions might not be caused by pressure alone. They might be triggered by structural failure, the comet literally breaking itself from the inside out. Picture it. A cavern deep inside finally gives way. The roof falls in, exposing gas, rich, amorphous ice. Sunlight or internal heat hits it. The gas expands, and suddenly you've got another explosion, visible all the way from Earth. It's less like a single soda bottle bursting, and more like an old building collapsing room by room, each collapse setting off clouds of dust. And this could explain why 29P's outbursts vary so wildly. Some are small, just a puff of gas and dust. Others are massive, ejecting 1,000,000 tons of material in a day. If the eruption is triggered by a tiny crack, you get a small show. If it's a whole cavern collapsing, that's when you see the comet flare hundreds of times brighter than normal. The idea makes 29P even more fascinating and more tragic, because it means the comet is in slow decline. Every eruption is not just gas venting, but part of the structure weakening, tearing itself apart piece by piece. It's a body in the middle of a long, icy death spiral, and we're lucky enough to be watching it happen in real time. And here's the haunting part. This slow-motion collapse could last for millions of years. Unlike a star that explodes once and is gone, 29P is unraveling gradually, in fits and bursts, like a glacier collapsing chunk by chunk into the sea. Each outburst is a reminder of how unstable it is and how little control it has over its own fate. But even with this elegant theory of cracking interiors and collapsing caverns, one puzzle remains. If the comet is falling apart inside, why does it erupt so explosively, so quickly, sometimes multiple times in the span of days? How does the pressure build up fast enough for these rapid-fire bursts? That's the mystery that still keeps scientists guessing. And it brings us to the heart of the problem. Even with all our theories, Centaur 29P is still far more violent than it has any right to be. Alright, let's pause and ask the obvious question. Why is Centaur 29P so violent? We get the basics. Amorphous ice traps gases. Crystallization releases them. Crust cracks, pressure vents, outbursts happen. That all makes sense on paper. But none of that explains the sheer ferocity of 29P's eruptions. Think about it. Most comets leak gas like a slow kettle boiling, a steady hiss. Maybe the occasional puff when they get close to the sundae, but 29P? It doesn't hiss. It doesn't puff. It detonates. Sometimes, multiple times in a row. Sometimes with debris flung faster than the speed of sound. These aren't little leaks. These are cosmic cannon blasts. And here's the kicker. The eruptions don't just happen once in a while. They happen dozens of times every year. That means the pressure isn't building up over centuries the way you'd expect. It's building up fast, unreasonably fast. Almost like the comet has a hidden mechanism for stockpiling gas and then letting it rip. One theory is that the comet's crust is stronger than we think. Instead of releasing gas in gentle trickles, the outer shell holds it in, like a stubborn cork jammed in a bottle. That allows pressure to rise far beyond the usual point before finally snapping. When it breaks, it doesn't just vent, it blows. Another possibility? Landslides and collapses. Remember, 29P's interior is slowly shrinking as amorphous ice turns crystalline. Whole caverns could be giving way. When a roof collapses, it could suddenly expose a fresh reservoir of volatile ice, triggering a massive eruption in an instant. There's also the idea that the comet's rotation plays a part. With a 57-day day, one side bakes in sunlight for weeks at a time. That's not just a tanning session, that's long-term heating. Long enough to destabilize weak spots until, finally, boom. But even with all these theories, astronomers admit they still don't fully understand it. The timing, the intensity, the rapid-fire explosions, it all feels excessive. Like the comet is overcompensating. And maybe that's the point. Maybe 29P isn't just another icy rock. Maybe it's teaching us that comets and centaurs are capable of far more violent behavior than we ever assumed. That the outer solar system, which we picture as cold and sleepy, can be just as explosive as a volcano on Earth or a lava geyser on Io. So the question isn't just, why so violent? It's, what else don't we know? Because if one icy centaur can act like this, who's to say there aren't others out there, waiting to reveal the same unruly streak? By now, you've probably realized something. Centaur 29P isn't just another icy rock in the outer solar system. It's a rebel, a cosmic outlaw. The kind of object that looks at the rulebook of comet behavior, lights it on fire, and then explodes 30 more times for good measure. Most comets play by the rules. They flare near the sun, fade in the cold, and repeat the cycle. Predictable, respectable, almost boring. But 29P? It sits in a circular orbit where nothing exciting should happen, and then throws tantrums like it's auditioning for a reality show. Astronomers love rules. They love models. formulas, predictability. And that's why 29P drives them nuts. It keeps smashing through every neat category we try to put it in. Centaur? Yes, but more active than any other. Comet? Sort of, but with a circular orbit instead of an elliptical one. Volcanoes? Kind of, but icy ones, erupting at random. It's a walking contradiction, or rather a tumbling, exploding snowball of contradictions. And that rebellious streak makes it important. Because the truth is, science doesn't advance when everything behaves as expected. It advances when something refuses to fit, when nature smirks and says, "Explain this, genius." 29P is that smirk. It challenges our assumptions about what icy bodies can do. It shows that eruptions don't need dramatic orbits or solar flybys. It proves that size, internal structure, and trapped volatiles can create a whole new category of chaos. And every outburst, every unpredictable blast, is a reminder that the solar system still has tricks up its sleeve. But beyond the science, there's something almost poetic about 29P. Out there in the cold, forgotten outskirts, this giant ice ball refuses to be ignored. It demands attention, not once a century, but every few weeks. A voice shouting in the cosmic silence, "I am here, and I am not quiet." And maybe that's why astronomers, amateurs, and professionals alike keep chasing it. Not because it behaves, but because it doesn't. Because it's proof that even in the places we think we understand, the universe can still throw us a rebel. If there's one running joke in the saga of 29P, it's this. The universe seems to prefer whispering its secrets to amateurs before it lets professionals catch up. Think about it. Time on major telescopes, Hubble, Keck, Webb is fiercely competitive. Astronomers spend months, sometimes years, writing proposals, defending their projects, fighting for just a few hours of precious observation time. And yet, who spots most of 29P's eruptions first? Not the scientists with PhDs, not the billion-dollar hardware. It's usually the amateurs. We're talking retirees in Spain, hobbyists in Arizona, people who set up backyard observatories because they simply love the sky. They sit under the stars with modest telescopes, night after night. And when 29P suddenly brightens, they're the first to notice. They post their observations online, sometimes in astronomy forums that look like they were built in 1998, and within hours, professionals scramble to react. It's humbling, honestly. Imagine being a career scientist, dedicating your life to planetary science, and then waking up to an email thread started by someone with a backyard Dobsonian telescope. "Hey, folks, 29P just blew again." The pros then have to beg for urgent telescope time to catch what's left of the show. But here's the beautiful part. It's not a rivalry, it's a collaboration. Amateurs provide the eyes, professionals bring the instruments. Together, they piece together the story of this chaotic comet. Without the hobbyists raising the alarm, many eruptions would be missed entirely. Without the pros, we'd never get the high-resolution data to understand what's actually happening. 29P, in a strange way, has become the poster child for this partnership. It's too unpredictable for scheduled telescope time, too erratic for neat scientific planning. But it's perfect for a global community of skywatchers who never stop looking up. And that's part of its charm. 29P doesn't care about prestige, budgets, or institutions. It explodes on its own schedule, and whoever happens to be watching gets the prize. Sometimes it's NASA. Sometimes it's Dave from Yorkshire with a 12-inch reflector. It's almost poetic, isn't it? This rebellious comet refuses to be owned by any one institution. Instead, it belongs to everyone, the shared obsession of a global crowd of stargazers. And while the collaboration is inspiring, it also underscores a bigger truth. Even with our best tools, there are limits to what we can predict, which brings us to the uncomfortable reality of 29P. Despite all we've learned, the mystery is still far from solved. Here's the hard truth. Even after nearly a century of watching Centaur 29P, after catching hundreds of eruptions, after throwing Hubble, radio telescopes, and even the mighty James Webb at it, we still don't really understand it. And that's not something scientists like to admit. Science thrives on clarity, on models that predict, on theories that explain. But 29P keeps slipping through our fingers, reminding us that the solar system isn't obliged to make sense. Think about it. We've explained some of the puzzle. Amorphous ice, trapped gases, circular orbit, cryovolcanic eruptions. But those explanations only take us so far. They tell us why eruptions happen in general. They don't explain why this comet erupts so often, so violently, and with so little warning. It's humbling, isn't it? We can map the motion of galaxies billions of light years away. We can detect black holes colliding in distant corners of the universe. And yet, a 60-kilometer ice ball right here in our solar system is still trolling us with random fireworks. 29P forces us to face the limits of prediction. It doesn't care about our neat schedules or models. Sometimes it erupts when conditions suggest it shouldn't. Other times, it stays quiet when every sign says it's about to blow. It's a reminder that the cosmos isn't a machine with a simple on-off switch. It's a messy, chaotic system full of surprises. And maybe that's the lesson. Science isn't about having all the answers. It's about learning to live with uncertainty and still trying. It's about chasing patterns, even when the patterns keep breaking. It's about amateurs with backyard telescopes spotting the unpredictable, and professionals building models that almost work, but not quite. 29P is a cosmic prankster, yes, but it's also a teacher. It reminds us that we're still students here, peering into the night sky with more questions than answers. And that's not failure, that's the whole point. If everything were predictable, science would be over. So the next time you hear that 29P erupted again, don't think of it as another unexplained outburst. Think of it as the universe winking at us, saying, "Still curious? Good, keep looking." If you've stuck with me this far, you've probably realized that Centaur 29P is more than just an icy object in space. It's a metaphor wrapped in a frozen shell, blasting its lessons across the cosmos with every eruption. Because let's face it, 29P isn't just science, it's philosophy disguised as astronomy. Think about the first lesson. Predictability is overrated. We humans love routine. We love knowing when the train arrives, when the sun sets, when the paycheck hits the bank. But 29P doesn't play by those rules. It erupts when it wants, how it wants, and as often as it wants. And maybe that's the point. Life, like 29P, doesn't always follow a neat orbit. Sometimes the surprises, the sudden flares, the unplanned chaos are the very things that make it worth watching. Second lesson, small voices matter. Remember how amateurs often spot 29P's tantrums before the pros? That's not just astronomy trivia. That's a reminder that curiosity isn't monopolized by institutions. Knowledge doesn't only belong to the people with million-dollar equipment. Sometimes it belongs to the retiree with a telescope in the backyard, or the kid staying up too late with binoculars. 29P democratizes discovery. It reminds us that wonder is a shared human trait, not a credential. Third lesson, change is messy. 29. P is literally tearing itself apart, mid-transformation. Amorphous ice collapsing, gas bursting, crust cracking. It's not stable, it's not graceful, it's not even remotely predictable. But that messiness is exactly what makes it interesting. Maybe the same goes for us. Transformation, whether in life, in societies, in ourselves, isn't smooth. It's full of eruptions and collapses. And maybe that's okay. And finally, humility. Because no matter how smart we think we are, no matter how advanced our telescopes, the universe will always have mysteries that outpace us. 29P is the frozen finger wagging at our arrogance. You think you know icy bodies? Ha, watch this. So what do we take away from this comet that won't calm down? Not despair, not frustration, but awe. Because in every unpredictable eruption, 29P is reminding us of the most important truth. We don't have it all figured out, and that's the joy of it. The universe isn't boring. It's alive, restless, dramatic, and sometimes explosively funny. And as we approach the end of this journey, there's one last thing to say, a closing whisper, if you will. Because 29P may be unpredictable, but there's one thing we can rely on, its ability to keep surprising us. And maybe, just maybe, that's all we need. So here we are, at the end of the trail, staring into the cold dark where Centaur 29P makes its home. After all the statistics, the theories, the missed Hubble shots, the amateur victories, the ice volcanoes and amorphous ice sponges, what are we left with? A mystery, a noisy, messy, beautiful mystery. Because if we're honest, we still don't really know why 29P does what it does. We've mapped the orbit, we've charted the eruptions, we've modeled the interior, and yet every time it explodes again, sometimes 4 times in 2 days, sometimes 5 in a week, we're reminded that the cosmos isn't here to obey our spreadsheets. It's here to surprise us. And maybe that's the point. 29P is more than an ice ball with a bad temper. It's a reminder that the universe is not finished teaching us humility. That even a 60-kilometer rock, barely bigger than a county back on Earth, can leave the smartest people on the planet scratching their heads. But there's something beautiful in that, something human. Because curiosity isn't about reaching the final answer. It's about chasing the questions, even when they keep running away. It's about the amateur astronomer who spots a flare at 3 in the morning, the graduate student writing yet another paper on amorphous ice, the quiet wonder you feel knowing that somewhere out beyond Jupiter a frozen body is exploding right now and no one can say exactly why. And that, maybe, is the lesson Centaur 29P leaves us with. That mystery isn't the enemy of knowledge, it's the fuel for it. That unpredictability isn't failure, it's the spark that keeps us looking up. So next time you glance at the night sky, remember this chaotic centaur. Somewhere out there, it's probably mid-eruption, throwing another icy tantrum into the void. And if you listen closely, in the quiet of the night, maybe you can almost hear it whisper. You don't have to understand me. Just keep watching.